Okay, hi again everyone. Welcome back to our Calculus 3 class notes. We're moving on to the last section in chapter 13. Remember 13 is we're talking about vector valued functions and motions in space. And in section 13.6 we actually want to talk about a different coordinate system, polar coordinates rather than rectangular coordinates. So we want to understand what velocity and acceleration in polar coordinates means to us. So first of all, before we do that, we need to understand what motion in polar and cylindrical coordinates are. So when a particle at position point, which has now the coordinates of it are r and theta, that moves along a curve in the polar coordinate plane, we express its position, velocity, and acceleration in terms of the moving unit vectors. So the unit vector use of r. So first of all, let me talk about remembering what polar coordinates are. Remember, polar coordinates for any point that has an x and a y coordinate. It also has a coordinate r and theta. So r technically is the square root of x squared plus y squared. And then theta comes from the tangent of theta is y over x. So theta is the inverse tangent of y over x. Hopefully you remember that from polar coordinates. But bottom line is r is the distance from the origin out to wherever the point is. And theta is the angle that is made with the positive x-axis, this angle right in here. Okay, so now when we talk about moving along a curve C, we now want to talk about this movement in terms of the vector use of r, which is a unit vector that's in the same direction as r, and use of theta, which is a vector that is perpendicular to use of r. Okay, inwards towards the curving. Okay, so use of r is cosine of theta I plus sine of theta j. And then use of theta is minus sine theta I plus cosine of theta j. So I won't take time to go through deriving exactly why those are what they are, but you can think of use of r. This would be x equals cosine theta and y equals sine theta, right? So this is minus y in the I direction plus x in the j direction. If we're talking about on a unit circle, and I don't want you to get too heavily involved in that. Just kind of understand what these unit vectors are in terms of r and theta. So the position vector in the r theta plane then, so remember r is x of r and theta in the I direction plus y of r and theta in the j direction. So that x, remember, is r cosine theta. Y is r sine theta. So then r is equal to r times the unit vector use of r. So this r, the position vector, is just however long it is times the unit vector use of r, which makes complete common sense, hopefully. So then if we add the vectors z in the k direction to the right-hand side, we are able to extend this position vector in just the r theta plane to a position vector in space using what are now called the cylindrical coordinates, r, theta, and z. So you can imagine, they're called cylindrical coordinates because you can imagine r and theta really comes from polar coordinates, from the circle down in the xy plane. And then if I go up a distance z, then r points from the origin up to that point. So it comes out in the r theta and then above that up z. So you can see how really, if you kind of revolve that, that looks like a cylinder, and that's why it's called the cylindrical coordinates. Okay, so then r then would be r times use of r plus z in the k direction. So now I'm trying to put it dimensionally here in 3 dimensions, where I'm comparing it to the x, y, z rectangular coordinate system. So, and that will now have r, which is r times use of r plus z in the k direction. Okay, so that's r use of r is out to here above that. So you can imagine this curve is rising up, maybe part of a helix or something like that. So this point on it then will have a unit vector in the direction of r, and then another unit vector in the direction of theta. And then it will also have a k component, which is going to be perpendicular to both of these guys. These guys are going to be parallel to the r theta, which is the same as the xy plane. So k will be sticking straight up. So we use the same unit vector in the z direction, k. So to determine the velocity and acceleration vectors, we need to take the first and second derivatives with respect to the parameter t, again, or time. So note 1, to make our work simpler in terms of notation, let's use the following shorthand. So u sub r dot is the derivative with respect to t of u sub r, and u sub theta dot is the derivative with respect to t of u sub theta. So just rather than having to write that every time, this makes it easier to put longer calculations in shorter notation. R dot is the r dt, theta dot is the theta dt. So the derivative with respect to theta of u sub r, right, is minus sine of theta in the I direction because u sub r was cosine theta in the I direction. So the derivative with respect to theta is minus sine theta. And then u sub r was sine theta in the j direction. So the derivative with respect to theta of u sub r is cosine theta in the j direction. Notice that the derivative of theta with respect to r is actually just u sub theta. Similarly, the derivative with respect to theta of u sub theta comes out to be minus u sub r.